All right, in the last section of chapter 10, we are going to consider a device called a generator. So we've seen in the previous video that if we change the magnetic flux, it will induce an EMF, an electromotive force, a voltage. So basically there's three ways to induce a voltage. We can change the magnetic field, we can change the area, and we can change the angle between the area vector and the magnetic field. The generator is based on that principle. We have a closed loop and there's a magnetic field passing through it, and we are turning the closed loop. Now generally the force needed to turn the generator is coming from some other form of energy. Most of the time, on this planet at least, it is coming from burning coal, natural gas, even wind turbine use that principle, hydro electricity in Quebec use that principle. We use some external force to turn a shaft, which will create a voltage. Actually, the only mode of producing energy that does not require some form of generator is solar power for now. So the basic principle here, basically, if we go back to the equation for the EMF, the equation for the EMF is equal to the number of turns of our closed loop multiplied by the change in magnetic flux. So the flux itself is given by magnetic field, area, cosine of the angle between these two. In this type of problem, magnetic field and area are constant. What change is the angle. So we need an expression that link the change of the angle with respect to time. And basically, the one we're going to use is the angle in radian, by the way, is equal to the angular frequency, so the change of the angle in radian per second, multiplied by the number of seconds, and to be very precise, we need to know the initial angle. So this is the initial angle, again, all in radian. So we take that formula, we replace our theta with this new expression, and we now have that term over here. Since it's a derivative with respect to time, we can extract all of the constant, namely B, A, we got our n number of turn over here, and we need to apply the derivative with respect to time to the cosine over here. So the derivative of the cosine is the sine, and we need to extract the constant in front of the time variable and put it in front. So W become in front. So we got electromotive force is equal to the number of turn multiplied by the magnetic field, multiplied by the area, multiplied by the angular frequency, multiplied by sine omega t plus the initial angle. What we will see is this will give something called an alternating current. As you can see here, the angle will change. The angle inside the sine will change over time, and the sine will fluctuate between -1 and +1. So there will be it will rise in voltage, reach a maximum, go down, reach a minimum, and go back, and so on and so forth until infinity. So if we were to plot the EMF with respect to time, what we will see is something like this: the voltage rise, fall, reach a minimum, and so on and so forth. The maximum it will reach is the multiplication of these four terms over here. And it's E0. So it's the number of turns multiplied by the magnetic field, multiplied by the area, multiplied by the angular frequency. So these four terms are equal to the maximum voltage it will reach throughout one cycle. So it will reach a maximum of plus E0 and a minimum of minus E0. All right. So in the next few examples, we're going to be solving some problem relating to this. This topic is not too complicated compared to the two other ones. It should go pretty smoothly. All right, see you in the next video.